Hello everyone, hello fellow computer science experts. It is Tommy again, welcome back. It's the second milestone of my project. It's a two-lane traffic simulation. To make this self-contained, this project is about a simulation of traffic. As you can see, let's visualize it. We have all the arrows representing cars, and each car is associated with a unique color, and cars are changing lane. To have a step-by-step view to understand how the cars are changing lane, we look at step I, where the red arrow or the red car has a motivation of changing lane to another because of the danger that is detected in front of its lead car, and then it changed at the next step suddenly to the next lane. Originally, I wanted to have a fair benchmarking, which is great, right? So to get a fair benchmarking, we need to have the cars giving them the equal chances of changing lane. And so we need to have a constant traffic density. And so when we're scaling the number of cars, we also need to scale the number of lanes. But in this second milestone, it turns out this is not necessary. To get a constant traffic density, all we need to do is just when scaling the number of cars, we just at the same time scaling the length of the lane. And this will restrict the model into a two-lane traffic only. It's simplified, it's optimized for GPU. To quickly explain again how the model works, we have two main tasks here, being trying lane change. Each car will detect its lead car and determine if its target position is going to collide with the lead car's target position. Okay, so determine target position, and then if there is a collision danger, then it tries to change lane given the safety of its adjacent lane. So that's the first task, and the second task is straightforward. First of all lanes need to resolve collision one by one. Okay, so resolve collision per lane, and after that, after collision is resolved, all cars are going to update its actual position given its target position. As I'm trying to parallelize it or optimize it, I realized that the three functions or the three subtasks here are parallelizable, namely determine target position and update actual position. They are parallelizable by the cars. And then the third function, resolve collision, is threaded by lane, so it's most intuitive to parallelize by threading the lanes. And then the second function, however, try lane change is non-parallelizable because that would result in different outputs compared to the CPU serial codes. Speaking of the codes, okay, let's look at the implementations I have. I have three of them here. The first one being the serial, very easy. So everything is serial, same logic. And then we have also the two GPU versions. At the first one, I took the convenience of using the abstraction of thrust library or CUDA thrust library. I did a combination of letting the thrust library manage my memory allocation and then also doing some manual memory allocation. So that's the second implementation. We're going to call it GPU thrust, although it's a hybrid method. And the third implementation is purely manual. Everything is manually allocated in terms of the matrices. Okay, so let's call it the GPU manual. And as you can see, the lane that is threadable, because we have only two lanes here in our model, I'm going to just thread with a fixed number of thread setting to 2. And then for the other two functions that are threadable by cars, we have a flexible number of threads. But at the initial implementation, I'm going to set the default number of threads to 4. With this one, let's look at a very easy CUDA n-side compute profiling. So let's restrict the number of cars to 500 only. It's easy to tell that tri-lane change, which is non-threadable, consume the largest compute and memory throughput, which result in the longest duration. This is followed by this lane threading resolve collision function. Okay. So once again, as I increase the traffic size, I will make it simpler to profile, I will just profile the two main tasks here, try and change and drive forward for each implementation. Let's look at them. So as I said, I started with the first scenario, which is 500 cars only. Going from CPU to GPU thrust, the good news and the bad news are, see, the tri-lane change has significant improvement with a complete different number being shown here, a different level of magnitude. So the runtime is significantly reduced. But the drive forward, unfortunately, is a vice versa. It gets terribly worse. With the GPU manual implementation, we compare it with the CPU. Now there's a good news. Both functions get optimized, and the optimization level is again a different level of magnitude. So I was quite happy here. Now let's look at a horizontal comparison. Okay, we just increased the traffic size with a doubling and doubling at each step. We realized that, okay, in the CPU code, the first function, tri-lane change, has an explosion as we increase the number of cars. This is actually explainable because the cars are trying to change lane here, but they don't necessarily change lane. With the increasing number of traffic, the chances of cars changing lane increase. And this if condition, as long as it is met, it will execute a much more complex instruction of changing lane. And therefore, the runtime explosion is non-linear. That is actually explainable. If we look at the second function, drive forward, there's no if condition that would enter, and therefore the increase of runtime is linear to the increase of traffic size. As we can see, the line is fairly straight here. So that explains our intuition, which is very straightforward. Now let's look at the GPU functions. We're looking at the thrust version and manual version. Having the tri-lane change and drive forward, I particularly hide the drive forward, and I'll explain later. We look at the three implementations here: the tri-lane change thrust, tri-lane change manual, and drive forward manual. All of them get not only optimized as we already originally compared with CPU, but also their runtime remains stable as we increase the traffic size fairly in a straight line. So that's utterly great news here. Now, the last one we see is the function that's in trouble here. The runtime explodes with the increasing traffic size. So not only doesn't it get optimized, it also explodes, which I'm not going to explain, but I'm going to summarize later. So let's summarize here. With CPU, the increasing traffic size, as I said, the more successful lane changes would give more instruction, therefore the tri-lane change runtime will explode. However, without such condition, in the second function, drive forward, we have the number of instructions being proportional to the problem size, and therefore the runtime increase will be linear. Let's look at the GPU again. To summarize it, what I learned here is thanks to parallelization in especially the CUDA manual version, we have the traffic size increasing and the runtime remains stable, which is great. And also the optimization is completely at a different level of magnitude compared to CPU. And unfortunately, the second function in the thrust version doesn't run as I expected, and I would suspect there are too much abstractions in the thrust library that I'm not able to profile and explain. With that, I also took a side experimentation of trying different threads in the CUDA manual version, and these two subtasks are the ones that are impacted by the number of threads, and we look at particularly only the first determine target position has an optimal, as I experimented, optimal number of threads being 64, and the second one doesn't have it. I suspect the reason is because of the complexity of the instruction in the determine target position with some arithmetics in it. There is something to optimize in here if we thread it and increase the number of threads. However, for the second function, we have the update actual position being too simple. It's just copying one memory to another, and therefore there's really nothing much to optimize here as we increase the number of threads and make it more parallelizable. So we can't see a lot of changes in the runtime. Lastly, I would like to thank all the instructors and the great tutors here in this course, namely Joel, Stephen, and Hugh, and others. I can't remember all the names, but thank you so much for providing this great learning experience, especially making it flexible for all students to do their own projects. Thank you.